Okay. So let me start again. So although only 3 quark flavors were initially introduced in the quark model, the up, the down, and the strange quark, we know today that there are actually 6 quark types, which come in 3 different generations. The first generation is up-down, the second is charm-strange, and the third is top-bottom, generational families. And each family has a quark with a charge plus 2/3. This is the same for all these up-type quarks, up, charm, and top. And a quark with a charge of minus 1/3, and this is the same for all these down-type quarks, so down, strange, and bottom. And of course, the corresponding anti-quarks have the opposite charges. Now, the 3 heaviest quark flavors, the charm, the bottom, and the top, were discovered later on, of course, in time, respectively in 1974, 1977, and 1995. And their mass is significantly larger than that of the UDS quarks. So the mass of the charm quark, the bare mass, okay? The bare mass of the charm quark is 1.27 GeV. So the charm quark itself is already heavier than the proton. The mass of the bottom is 4 GeV, so 4 times the mass of the proton. And you see here the mass of the top is something really incredibly high, something like 173 GeV. So approximately 200 times the mass of the proton. And it is the reason why it took 20 years to detect the top quark after the first 2 here. So we will discuss about the discovery of the top quark later on in the weak interaction chapter. We will come back to that later. So let me first start with the charm quark. The first experimental proof of the existence of the charm quark arrived in 1974. Where 2 different experiments presented simultaneously evidences for the formation of a C-bar meson that is today known as the J-psi meson with a mass of approximately 3,100 MeV. So the first experiment was performed at SLAC in California at the SPARE facility. And essentially, they were colliding E+ and E- beams. And at a certain point, they found events where some intermediate objects were created that they called psi, which was eventually decaying into, again, electron positron or mu+, mu- or hadron pairs. And indeed, simultaneously, in the same days, in the same period, essentially, another experiment that was performed at Brookhaven National Lab with the AGS machine. They did, essentially, they were scattering a proton beam over a beryllium target. And in a certain amount of events, they found that a new object was populated that they called J, which was eventually decaying into E+, E- or other final states, plus anything else. So other particles producing the collision. Now, since the 2 experiments arrived in the same time, simultaneously with essentially the same discovery, today we call this particle J-psi, okay? Now, just to show you some pictures. So this is Samuel Ting, who got the Nobel Prize in 1976, together with his colleagues, showing, you see here, the J resonance, okay, that they found at BNL in 1974, decaying into E+, E-. So there is a huge peak, a huge resonance indeed at the mass of just a little bit above 3 GeV. And this guy here is Burton Richter, who shared the Nobel Prize with Samuel Ting for the discovery of the J-psi meson, indeed. And you see here now the results from the SLAC experiment, where you see here a resonance that they call psi decaying into electron positron or mu+, mu-, or hadrons, mu+, mu-, and electron positron. Okay. Now, the J-psi is only, let's say, one of the many states of the family of charmonium states. Okay, so all these states here are bound states of C-bar quarks. Okay, of course, with different quantum numbers. You see here, for instance, the JPC quantum numbers in the bottom, and also the value of the orbital angular momentum. So it is essentially a spectrum of several different excited states, the ground state being the eta-C. And the structure of the charmonic excited states can be obtained, can be studied by solving the Schrödinger equation, so the non-relativistic equation of motion, with this kind of potential. So the reason for this kind of potential we will understand better next week in the framework of QCD. But nonetheless, here we have essentially two different contributions. One is a Coulomb-like contribution that goes like 1 over r, which is dominant at short distances. And then there is a linear term, which is proportional to the distance, which is instead dominant at larger distances. Okay, so we will derive this potential next week in the frame of QCD. Why non-relativistic? Because now the C-quark are relatively heavy objects. Okay, so in a sense they move slower than the light quarks, and so a non-relativistic approach is quite accurate. Okay, for this kind of studies. Now, soon after the discovery of charmonium, also a combination of light and charm quarks were discovered that today we call the D mesons. And this can be categorized according to their different quantum numbers. So the JP D mesons, JP equals 0 minus, so pseudoscalar, are those that you find here. So the D0 is a CU bar object, then we have the antiparticle, UC bar, then we have the D plus, CD bar, etc. And also those involving the strange quark, so CS bar or SC bar, etc. Then we have the charmed vector D mesons with the quantum numbers 1 minus that are denoted with this star here, D star 0, D star plus S, etc. And then, of course, there are possible radial excitation, so with higher value of angular momentum, etc. Now, what is the consequence of the discovery of a fourth quark in our discussion, so in the framework of the quark model? The addition of a fourth quark, that is the charm indeed, would bring in principle to an extension of the SU3 flavor symmetry to an SU4 symmetry. However, as you can already imagine, this symmetry is strongly broken because the mass of the C quark is now much higher than the mass of the 3 quarks, and it is actually comparable with the mass of baryons themselves, the order of 1 GeV. So although the SU4 flavor symmetry is indeed a very approximated symmetry, it is still useful for classifying baryons and mesons containing one or more C quarks. And these hadrons can be indeed grouped into new multiplets. So there is a more complex multiplet structure, as we will show, which is now displayed in a three-dimensional space, which is spanned not only by the I3 and strangeness, or I3 and, let's say, the hypercharge that we studied so far, but also we have an additional dimension, which is the charm. Okay, so let's see indeed what happened here. So once we include the fourth quark, in order to create baryon and meson multiplets, we have to combine a quark quadruplet together with, this is for mesons, okay? So a quark quadruplet with an anti-quark quadruplet, okay? And once you do so, then at the end you obtain a 16-plet. I don't know how to call it better than this, okay? Which it is in the space organized in this way. So we have the strangeness in this axis, the third component of isospin in this axis, and the charm in the vertical axis. So it comes with like a three-floor object. And this we can see even better in the next slide. So these are indeed the mesons, also considering the C-quark mesons. We have a 16-plet with JP 0 minus, so pseudoscalars, and a JP and 16-plet with JP 1 minus, which are the vector. And then, of course, we have also excited states that are not reported here. And here, if you now look at the central plane, you recognize what we know already from SU3. But it is nothing else than the SU3 meson nonet, so the octet plus the singlet, plus there is just only one new object, which is the eta C, which also lies in this plane here. Okay, and similarly for the vector meson. So again, this is our in this plane we recognize the vector octet plus singlet plus in addition the jet psi. What about baryons? Okay, we can do the same game also for baryons. So in this case, we have to combine three quark quadruplets. And the result is, by group theory, that one should expect a 20-plet, which is fully symmetric, a 20-plet, which is a mixed symmetry, a 20-plet with a mixed asymmetry, and a quadruplet with completely asymmetric. Okay. So in particular, here you see the two twin triplet for the JP 1/2 plus and JP 3/2 plus. Okay, so the scalar and the vector baryons. Again, the structure is pretty complex, and it is now displayed in this three-dimensional space spanned by the three quantum numbers, essentially. And again, now in the first floor, we recognize the SU3 baryon octet, okay, and the SU3 baryon decuplet for the case of spin 3/2. Let me just note that not all of these states have been discovered yet. For instance, the Xi CC double plus charge was first observed 4 years ago by LXCB, okay? And as far as I know, still this object is not discovered yet. So it is predicted by the symmetry, but it's not yet discovered, and I'm not sure about those two here. So all this was about the C quark. What about now the bottom quark? So the story was somehow similar, but now 3 years later. So the bottom quark was also discovered in the form of a bound state of B bar quarks, okay, that was called the Upsilon meson, actually Upsilon mesons, because there are many, of course, depending on the quantum numbers. And these were discovered at Fermilab with a mass range in the order of 9.5, 10.5 GeV. So of course, these objects are much heavier than the charmonium states. And in this discovery that you see here, the very first observation of this object, okay, around 10 GeV, this proved the existence of the bottom quark. And as for the charmonium, we also have a family of excited states of the bottom of the BB bar bound state that we call the bottomonium family. Okay, the ground state is this eta B. The upsilon that was observed here is this that stays here, which come in a cascade of decays from upsilon 3s, upsilon 2s, and upsilon 1s that eventually decays into the ground state. And also in this case, one can study and one can actually reconstruct these excited states by using the non-relativistic Schrödinger equation with the potential that I showed before. And this is even more suitable here because the bottom quark is even heavier than the C quark. So the non-relativistic approximation is, of course, even more valid in this case. Now, as for the C quark, the discovery of the upsilon mesons was soon followed by that of the B mesons, which are a combination of the B quarks or antiquarks together with lighter quarks. So the B0 is a DB bar, the B0 bar is a BD bar, etc. Okay, you also have with strange quark and also in principle with C quarks involved. Now, similar multiplets of mesons and baryons can in principle be constructed in a 4-dimensional space. Now, if we also want to extend our flavor symmetry to include also the B quark, so this will become an SU5 flavor symmetry, which of course is extremely broken. It is extremely approximated and broken. Okay, so it has not really any usefulness in this case. Nonetheless, it is useful to introduce the corresponding quantum number that is related to the number of bottom quark that you have in your hadron that we call beauty. And we indicate with this tilde just to distinguish this quantum number with the baryonic number, which is also denoted by the capital B. So this additional quantum number is introduced to account for the number of B quarks in your hadron. And now what about the top quark? So the top quark is a completely different story. It is essentially too heavy, as I was mentioning before, is a mass of 173 GeV, okay? So it is itself heavier than the golden nucleus by its own, and it is extremely unstable due to this large mass, okay? So the decay time is of the order of 510 to the minus 25 seconds. So in no way the top quark can be bound in a hadron state. It can be produced in very high energy collisions, but then it decays immediately and can never take part of any bound state. Okay. Nonetheless, for completeness, one can also define the corresponding quantum number that we call the truth, and we indicate with the capital T. Okay. However, since of course no hadrons contain the top quark, then the truth quantum number is always 0 for all hadrons. Now we can extend our concept of hypercharge. We defined the hypercharge at the beginning when only the strangeness was introduced, okay? As it was basically introduced in the original version of the flavor of the Quark model. But now, of course, we know that we have 3 additional Quark flavors, okay? So we can extend our definition of hypercharge to include all of them, okay? So the hypercharge is the baryonic number plus the strangeness plus the charm plus the beauty plus the truth, okay? And it is related to the electric charge of our hadron by this relation, which also includes the third component of isospin, okay? So this formal relation is the same as we have seen before, but now epsilon also include all the other flavor, the Quark flavors, quantum numbers. So we can now summarize all we know about these quantum numbers. So the first component of isospin we can obtain by this simple formula. So it's the number of up quark minus the number of anti-up minus the number of d quark plus the number of anti-d quark. The strangeness we already defined as the number of strange minus the number of anti-strange with an opposite sign. And now we can also complement these with the charm, the beauty, and the truth, okay? Which are given, of course, in the same way. With the only thing to be attention to be paid is the sign here, okay, which is minus for the strange at the bottom and plus for the charm at the top, and these reflect the electric charge of the strange bottom and the charm top quark, as we will mention in a moment. And then we can generalize also our definition of the baryonic number, okay? So the general definition is 1/3 of the number of quarks minus the number of anti-quarks. So it is always 0 for mesons. But now we can make this more explicit. Okay, so this is the number of U quark minus the number of anti-U plus the number of D minus the number of anti-D minus strangeness plus charm minus beauty plus truth. All these divided by 3. So about the sign that I was mentioning before, by convention, the sign of the quark flavors is the same as that of the electric charge. So it is positive for all the up-type quarks, so for what concerns us from the charm at the top, and negative for the down quark tops. Okay, so from the strange and the bottom, the beauty and the bottom. Now, all these quantum numbers, which we call together the internal quantum numbers, okay, are all conserved by electromagnetic and strong interactions, but as we will study next in the course, they are violated. Okay, they are not conserved by weak interactions, because weak interactions allow for flavor changing processes. And the most golden process that you, of course, know is the beta decay of a neutron into a proton, where, for instance, a down quark is changed into an up quark, etc. We will study this in detail in the weak interaction chapter of the course. So let me summarize now on this table the main properties of the 6 quarks. So in the first column we have the mass, okay, as we already discussed. Then we have all these internal quantum numbers that are the charge, the baryonic number, the hypercharge in the full definition, and then third component of isospin, strangeness, charm, beauty, and truth. Okay, so it is pretty obvious that if you take the charm quark, it has a 0 isospin, 0 strangeness, 0 beauty, 0 truth, but it has some value for the charm, and the same for the others. Okay, keep also attention to the minus sign for the strangeness and for the beauty. And we have the analogous table for the anti-quarks, okay, where essentially, of course, the masses are the same as one would expect based on the CPT theorem, but all these internal quantum numbers are just opposite. So switching from the particle to the antiparticle is not only changing the sign of the electric charge, but it is changing the sign of all these internal quantum numbers. Now we can also summarize a few examples of hadrons. So we have baryons and mesons here. So here we have the masses. You see that they vary a lot as soon as you introduce a charm or bottom quarks. And then we have the charge and also these all these quantum numbers. Okay, so you can check all of them, but let me just concentrate on one just as an example, the sigma plus C. So let's now solve this trivial exercise just to get familiarity with how to deal with these quantum numbers. So determine the internal quantum numbers, so the Fourier quantum numbers, hypercharge, baryonic number, and electric charge of these Xi C plus baryon. So we're going to have to calculate all these quantum numbers here. So let's move to the board. Any question so far? Okay. So this is problem 510. So the particle we want to study is the Xi plus C, which is a USC bound state. So let's start with isospin. Okay, of course, I mean, all these quantum numbers are trivially deducible from the quark content, but let's make it nonetheless the full calculation just to get familiarity with this. So the third component of isospin is in general 1/2 number of U quarks minus number of U bar minus number of D quarks plus number of D bar quarks. So we have 1/2. Then we have 1 up quark, 0 U bar, 0 D, and 0 D bar. So overall it is plus 1/2. Okay, as one would immediately say just by considering that there is only just one up quark. What about strangeness? This is minus number of strange quarks minus the number of anti-strange quarks. So it is minus. We have 1 strange quark and 0 anti-strange, so it is -1. Then we have the charm. This is the number of C quarks minus the number of C bar quarks. It is 1 minus 0, it is 1. Then clearly we don't have bottom nor top quark, so the beauty, which is number of bottom minus number of anti-bottom, is just 0. And same for the truth, it is number of top minus number of anti-top, of course, this is 0. What about baryonic number? So let's use the full formula. So it's 1/3 number of U minus number of U bar plus number of D minus number of D bar minus strangeness plus charm minus beauty plus truth. So this is 1/3, and then we have 1 minus 0 plus 0 minus 0 minus -1 plus 1 minus 0 plus 0. So overall this is 3/3, it is 1. Of course, this must be 1 with just one baryon. Then we can calculate the hypercharge as baryonic number plus strangeness plus charm plus beauty plus truth. And this is 1 plus -1 plus 1 plus 0 plus 0, which is +1. And finally, we can compute the electric charge, which is obvious just by looking at our baryon, but nonetheless, let's use the full formula. So it's third component of isospin plus half of the hypercharge. So we have 1/2 plus 1/2 equal +1. Okay, pretty simple. Now, let's move on to the slide again. All right. Okay. So nowadays, we are in 2021, many hundreds of particles have been discovered, of course, since the 50s, so since the advent of the high-energy accelerators. And the question is, how can we remember all of them and all their properties? The mass, the charge, the spin, internal quantum numbers, decay modes, branching ratio, etc. And once Enrico Fermi said, if I could remember the names of all the particles, I'd be a botanist. And he was right. So we are lucky because there is a very useful tool for us that is the review of particle physics. So it is essentially a book, okay, order of 2,000 pages. It is also known as the particle Databook. And this can really help us to find all the properties that we need for any observed or even non-observed particle. So this is edited by the Particle Data Group, or in short PDG, which is an international collaboration of about 150 particle physicists that compiles and organizes every year published results related to the properties of particles and fundamental interactions, and reviewing in addition also the theoretical advances relevant to experimental physics. So the PDG publishes every 2 years the review of particle physics and also its pocket version, the particle physics booklet. And it updates annually, every year, the information on the PDG website. So what is in? So the review of particle physics is in the form of a journal publication, and it appears in different journals, depending on the year. And currently, it is the most referenced article in high-energy physics, being cited by more than 2,000 times per year in scientific literature. It is divided in 3 sections. So the particle physics summary tables, which are tables with the main properties of all known particles. This is divided into bosons, mesons, baryons, etc. The review tables and plots. So the review covers many related fields that span from mathematics to statistics to current status of the standard model searches, search for new physics beyond standard model, cosmology, relativistic kinematics, whatever, okay? So there is a huge documentation provided in this book on all these subjects. And then there is the particle listings. It is an extended version of the summary tables, which include the references to all the experimental measurement. And this section contains all the relevant data that are published in journal, okay? And from this data, the PDG collaboration elaborates world averages, okay, for the main properties of the particles. The particle physics booklet, it is just a condensed version of the review of particle physics. It includes the summary tables and, let's say, a shortened section of reviews of the review table and plot. Now, this is how they look like. So this is the last edition, so from 2020. The next will come next year. This is actually every 2 years, as I was mentioning. So this is the review of particle physics. Is something like 2,100 pages. And this is the cover of the booklet, which is only 300 pages approximately. Okay. And this is the website. So you can click here and you can get into this realm, okay? You can also, so you can navigate into all the tables, all the reviews, whatever you want here. And I think you can also request a booklet, so you can get it by email, by mail. You can download for sure the PDFs. Now, okay, it's still early. Okay, but that will be a rather shorter lesson. But okay, let's move on. Okay, so do you have questions about this? Okay. Then let's continue. So let me come back again to the concept of hadronic resonances. We have touched this subject several times already in the course. Today we will go into some more detail. So let me just recap that the lifetime of hadrons that can decay strongly is extremely short, as you know, with a decay time of order 10 to minus 23, 24 seconds. From the experimental point of view, it is therefore impossible to reveal their tracks because they are too short. Okay, in a sense, they are seen to decay exactly where they are produced. The extremely unstable hadrons can be instead observed in the form of resonances. Okay, so let's now study what resonances are and how to deal with them. So first of all, resonances can be observed in two different ways. The first way is so-called information. Okay, so suppose you are colliding two particles A and B, then you form a resonant state which eventually decays into final state particles. Okay. And if this kind of mechanism occur, then you would notice this by a bump in your cross-section when you plot the cross-section as a function of the center of mass energy. Okay? And the bump of the cross-section would correspond to the mass of this intermediate object. The other way is in production. Okay, so in this case, you are still colliding two particles A and B, but you produce a resonance together with other particles, and then the resonance decays into its final state. Okay. In this case, you can reveal the resonance by plotting the invariant mass, okay, of the two final state particles. Okay. So suppose you are able to measure the energy momentum, you can reconstruct the invariant mass. You can plot this, the distribution of invariant mass, and then you find a peak, okay, which corresponds to the mass of this object here. Now, let's first study the production process, okay? So this second one. Let's consider a generic reaction, A plus B, that goes into C plus D plus E, okay? Now, if an unstable particle R exists, which can decay into C plus D, then in a fraction of cases, the reaction above proceeds through an intermediate state containing the resonance R. So we call this a resonant process. So the process could be A plus B that goes into R plus E, where R, which is the resonant state, eventually decays into C plus D. So at the end, the final state will be the same as you would observe here without the population of this intermediate state. E plus C plus D. And the invariant mass of this C plus D system should be around the mass of our resonant object. Let's just study one example, okay? There are, of course, plenty of examples. So let's consider this example. So let's consider the reaction of a K minus proton that goes into lambda 0, pi plus, pi minus, okay? So one such reaction was studied in the 60s through a bubble chamber filled with liquid hydrogen and exposed to a 4 GeV K minus beam. And so you see here the event that has been photographed by in the bubble chamber, which was immersed in a magnetic field, of course. So you see here the incoming K minus. At a certain point, this K minus was interacting with one of the protons of the bubble chamber, okay? This hydrogen that was filled, and the reaction occurred. So we observe here a pi plus, a pi minus, and something neutral that is not observed in the bubble chamber, which further decay into a pion and a proton, okay, which is indeed the lambda 0. Now, the same reaction, however, can also proceed in principle through an intermediate state, actually with a very high probability or a very high cross-section. In this case, two new resonant states can be formed, okay, each corresponding to a new particle and both leading to the same final state. So let's see how. One possibility is the following. The K minus with proton interaction provides a sigma star plus pi minus, where the sigma star plus decays into a lambda 0 pi plus, and the lambda 0 further decay into a proton pi minus. Or you can have the other possibility. Still the same beam, still the same target, but now you create a sigma star minus and a pi plus. So the electric charges are just swapped here. As a consequence, this sigma star minus can decay into a lambda 0 pi minus instead of pi plus, and the lambda 0, as usual, into a proton pi minus. If this happens, then the invariant mass of the lambda 0 pi plus and lambda 0 pi minus system should peak around the mass of the sigma plus or minus, okay, which is the order of 1,400 MeV. Okay, so let me show you something on the board. So let's consider indeed this sigma star plus or minus resonance. So the invariant mass, as we studied in the very first lesson, okay, for the lambda 0 pi plus, okay, it is given by the mass shell relation. This should be equal to the square of the four momentum, and the square of the four momentum we can develop as E squared lambda 0 pi plus minus the square of the three momentum lambda 0 pi plus. So let's make this more explicit. So this is the total energy of the lambda 0 plus the total energy of the pi plus squared minus the three momentum of the lambda 0, is a vector, plus the three momentum of the pi plus squared. So this is equal to E squared lambda 0 plus E squared pi plus twice E lambda 0 E pi plus minus P squared lambda 0 minus P squared P plus minus twice the scalar product P lambda 0 scalar P pi plus. Now we can collect the energy and momenta for the same particle. So E squared lambda 0 minus P squared lambda 0 plus E squared pi plus minus P squared pi plus minus twice the product of the energies, E lambda 0, E pi plus, minus twice. Now we can develop this scalar product. So we have the product of the two momenta times the cosine of the angle lambda pi, theta lambda pi. Now, this is, as you know, the squared mass of the lambda 0. This is the squared mass of the pion. And so we have m squared lambda 0 plus m squared pi plus twice. Then we have E lambda 0, E pi plus minus P lambda 0, P pi plus cosine of theta lambda pi. Okay, so experimentally one needs to measure the moduli of the momenta. So this guy here. And this you can do, of course, by measuring the trajectory of the charged particle in the magnetic field, okay, the curvature radius, and this angle here, okay, that you can also infer from the photograph of the bubble chamber in that case, okay. So you need to measure the two momenta and the angle between them. Concerning the energies, of course, you have also to measure the energies, and this you can deduce a posteriori after you measure the momenta, okay, and you know the masses, okay, so just by applying the relativistic relation. And so at the end, when you look at your data, what you find is should be something like this. So here you put your invariant mass of the lambda 0 pi plus. Here you have the number of events, for instance, and then you see something. There is some background. Then there is a sharp peak, and then again your background. And your sharp peak, of course, should correspond to the mass of your sigma star plus or minus. Okay. So let's come back to the slide now. All right. So there is an easy way, an easy technique to check if this reaction proceed or not through an intermediate resonance state. Okay, and this is by making use of the so-called Darius plot. The Darius plot are two-dimensional plots with the squared invariant mass of two particles in one axis and the squared invariant mass of the other combination of particles in the other axis. For instance, one in the y-axis, one in the x-axis. Okay, and so we will now show how this technique is applied to this reaction, but this technique is very general and can be applicable to any three-body reaction or decay. So let's look like to this Darius plot. So in this example, in the x-axis, we have the squared invariant mass of the lambda pi minus pair. And in the vertical axis, we have the squared invariant mass of the lambda pi plus pair. Okay? So we have three objects in the final state. You pair 2 by 2, and you plot the squared invariant mass in the two axes. Now, a few comments on what you see here in the plot. So first of all, the use of the squared mass rather than the mass themselves in the Darius plot is motivated by the fact that the phase space is uniform if you take the squared masses. And this is extremely useful because if you do observe any non-uniformity in this plot, then this is a clear signal of something dynamical. So, for instance, the population of an intermediate resonance state, as we will see in a moment. Okay. Otherwise, it is pure phase space. It's pure kinematic. If you don't see any accumulation of points somewhere, then this is just pure kinematics. Okay, pure phase space. The contour line that you see here, okay, is that line here, delimits the region allowed by energy and momentum conservation. So you cannot have events outside this because they would violate energy and momentum conservation. Now, suppose that indeed these two resonance states are populated, okay, through the reaction as an intermediate state. Then indeed, if you construct your Darius plot, you would observe some accumulation of data in some points. Okay. In particular, as you see here, there is an accumulation of data that when you project in this axis, you obtain indeed the mass of the sigma, which is 1,385. See, this one, just a little bit below 1,400 here. And the same if you project now these into this horizontal axis. Okay, also here you get the mass, which is the same value here. Okay. Of course, when you project all your events into one single axis, you would get the real resonance, okay, corresponding to the real mass, plus another bump, which is not physical because it is just the reflection of the other resonance, which should be instead obtained by projecting these other axes here. Okay, so one should not be confused if you see more than one peak, because typically the other, which are broader, are only reflections of other resonances, but not new real states. Now, the lifetime of the resonance state is typically of the strong decays and can be estimated by the width. So once you have your resonance, you can calculate the width at half maximum, okay, our gamma. And indeed, for the case of the sigma star plus, it is of the order 100 MeV. And so we can compute the decay time in the way we know already, okay? And in fact, we realize that it is a typical of strong decays. So it is an atom which is decaying strongly here. Okay, any questions? Okay, if there are no questions, I propose to stop now for, let's say, 7-8 minutes, and we recombine at 12. Ok? Mi date un segno che esistete? Ok. Vabbè, riprendiamo alle 11. Ok, possiamo riprendere. Dunque, vi siete quasi dimezzati rispetto all'inizio del semestre, siete rimasti in 7 praticamente. Allora, siamo alla slide. Ok, mi sentite? Vedete la slide?
Sì.
Okay.
Sì.
Bene. Okay, so we discussed a nice example of resonance in production. Let's now move to the other mechanism, that is the formation mechanism. Okay. So let's now consider a fixed target collision between two hadrons. Now, the incident hadron has a de Broglie wavelength lambda, which is inversely proportional to the momentum. And the target hadron is, of course, at rest in the laboratory frame. Now, if by varying the energy of the incident particle, so in other words, by varying the center of mass energy of the reaction, a maximum of the cross-section is observed for a given value of lambda, and of the relative orbital angular momentum L, then a hadronic resonance has been formed. Hadronic resonance is characterized in general by a mass corresponding to the total center of mass energy at the maximum of the cross-section, a specific value of the angular momentum, a definite parity, a definite isospin, etc., and also a definite width, which corresponds to a definite lifetime. In the proximity of a resonance, the shape of the production cross-section follow a Bright-Wigner function, okay, which is this shape here you see. And the decay width, the gamma, which is inversely proportional to the decay time, is obtained simply by the full width at half maximum of the peak. Okay. Now, let's consider first of all stable particles. So stable particles are described by pure harmonic wave function versus time. So the time dependence of the wave function for a stable particle is just an harmonic or sinusoidal. Okay. And in particular, so we can write it this way. This is the time dependence. In particular, if you are in the rest frame, the energy is just the mass rest energy. Now, since energy and time are conjugate variables, one can always obtain the center of mass energy dependence of the wave function by Fourier transforming the time dependence of the wave function, okay, because the two are conjugate. So suppose you know your time dependence, which is of this kind here for stable particles, then you can obtain the center of mass energy dependence of the wave function by Fourier transforming your time dependence. Okay, so you can just substitute here, and you have to solve this Fourier transformation here. Now, it turns out that Fourier transformation of pure harmonic wave functions are functions which are centered at a very well-defined energy value. Okay, so essentially they are a delta Dirac at a specific value, which is the value of the mass in this case. Okay. So if you have a totally fluctuating time dependence, you get a sharp energy dependence as a consequence of the uncertainty principle, of course. What about now unstable particles? So unstable particles are described by damped harmonic wave functions because of course they decay in time at a certain point, and the proper energies are not well defined in this case. So we don't have anymore a delta Dirac here, but we have a certain distribution with a certain width around the mass of the particle. Okay. The time dependence of the wave function for an unstable state must include a damping factor, okay, to allow for this exponential decay here. So let's look this into more detail on the whiteboard. All right. So if the resonance is an unstable particle, its surviving probability must follow the standard exponential decay law. So we know that for the standard exponential decay law, for decaying particle is n0 is nt equal to n0 times c to the minus t over tau, right? So the number of particles that survive at a certain time t is equal to the total particle at time 0 times this damping exponential factor, where tau is the decay time. Now we can translate these in terms of wave function or better into probabilities. So this essentially is equivalent to writing that psi over t squared is equal to psi at time 0 squared times e to the minus t divided by tau, which is equivalent to write psi 0 squared times e to the minus gamma t. Okay, well, of course, gamma is in natural units, is just the inverse of the decay time. Now, this can be achieved by, so we have to include this damping factor, okay? So we have to end up with this exponentially decay probability, and this can be done by including a damping decay factor into the time dependence of the wave function. So for unstable particle, the time dependence of the wave function should look like this, e to the minus I t times e to the minus gamma divided by 2t. This is our exponential decay factor. And in the rest frame, of course, the energy is just the rest mass energy. So this is just e to the minus I mt times e to the minus gamma divided by 2t. So that's why this is indeed the correct damping factor that one should use. And this we immediately recognize when we calculate now the probability of square modulus of our wave function. It is psi star psi. It is proportional to e to I mt, this is the complex conjugate, so it comes with a plus sign, the exponential, times e to minus gamma half t, this remains negative because it is a real exponential, times e to minus I mt times e to minus gamma half t. Okay. And now in the product, of course, these two oscillating term disappears, and one is just left with e to the minus gamma half plus gamma half t, so e to the minus gamma t, okay, which is exactly what we need in order to describe correctly our exponentially decaying probability. Now, since, as before, the energy is the conjugate variable of time through the energy time uncertainty principle, then, as I was mentioning before, one can always obtain the center of mass dependence of the wave function by Fourier transforming the time dependence. So, as I was showing before on the blackboard, on the slide, you can calculate now the corresponding center of mass energy dependence of the wave function by Fourier transforming the time dependence. Okay, so we can now substitute. So this is e to the minus I mt times e to the minus gamma half t times e to the minus I e t in the t. Now this is a known integral. It can be solved analytically, and the result of this is E1 divided by E minus m plus I gamma divided by 2. So this is now the center of mass energy dependence of our wave function for an unstable particle, okay, which of course takes into account this exponentially damping factor. Now this is the wave function, but of course we are interested in the probability. So because the reaction rate or the decay rate or the cross section, whatever, of course goes with the probability. But essentially, when you now square this, the result is 1 divided by m minus e squared plus gamma half squared, that you can also write in equivalent way as 1 divided by er minus e squared plus gamma squared divided by 4. Okay, where er is the value of the mass at the resonance. And this particular functional form is known as Breit-Wigner. Sorry. Okay. So now this is, let's say, the formalism. Let's now take an example that we already discussed in the past, that is the delta plus plus resonance. So let me now go back. No, okay, yeah, to the slide, yes. First of all, let me add something here. So let's consider the elastic resonant process, where elastic means that the final state particles are just the same as the initial state, where the prime indicate that, of course, they come with a different moment, okay, and different angles. Now, for a resonance of a specific angular momentum J formed in elastic collision, such as this one, of the two particles A and B with spin SA and SB, the cross-section in correspondence of the resonance has indeed this Bright-Wigner shape. This is exactly the term that we calculated on the whiteboard, okay? And what we have on top of this is just the spin multiplicity. We have the J of the resonance and the spin of the two incoming interacting particles, and then some kinematic factor on top of this, okay? So this is the shape one would expect in proximity of the resonance. So as I was saying before, let's consider now again once more the delta plus plus resonance that we discussed already several times. These you can populate in any of these pion-nucleon elastic or charge exchange reactions. Let me remind you that this is the total pion-nucleon cross-section, which includes the elastic and the inelastic, and this is only the elastic contribution, which goes to zero as soon as you increase your energy. But at low energy, okay, essentially everything is elastic, so the two coincide here, and you indeed populate this huge resonance, okay, at the mass of 1,232 MeV, so right here, and with with the half maximum of 120 MeV. And of course, the spin of the incoming proton is 1/2, and the spin of the pion is 0, the absolute scalar. Okay. So let's now apply to this well-known resonance our formula of the Bright-Wigner. And let's now calculate indeed the value of the cross-section in correspondence of this resonance here. Okay. So this resonance is populated by elastic pion-nucleon scattering. Okay, so what we need is indeed the elastic shape of the cross-section, which depends in general on the energy and on the angular momentum. So this is 4 pi. Then we have the reduced de Broglie wavelength squared. Then we have this spin multiplicity factor, 2J plus 1, and then we have 2s of the proton plus 1, 2s of the pion plus 1. And then we have the Bright-Wigner term, which is gamma squared divided by 4. And then we have the value of the resonance energy minus the center of mass energy plus gamma squared divided by 4. So let's substitute what we know already about this resonance. So this is 4 pi, then this we can still copy. Then we have 2J plus 1 on the numerator, but we can already substitute the spin of our incoming particles. So the spin of the proton is 1/2 times 2 becomes 1 plus 1, 2, times the spin of the pion is 0, so just times 1. Now we can also substitute the numbers here. So the width at half maximum is 0.120 GeV squared divided by 4. Here we have the mass of the resonance, so it is 1.232 GeV minus the center of mass energy squared plus again 0.120 GeV squared divided by 4. Okay. Now let's assume for the moment that the angular momentum of the resonance is 3/2. We will justify this choice later on. Okay, so let's assume this for the moment. So when we substitute now 3/2 in place of J, and we consider now the cross-section at the resonance, so with the ECN exactly equal to the mass of the resonance, okay, then it happened that this guy in the denominator goes away. And so we have down the numerator is equal to the denominator. So this whole factor here is just equal to 1 at the resonance. Okay? And so we are left with sigma L at the maximum as 4 pi. Then we have the square reduced derivative length. Then we can substitute here 3/2 in place of our J, divide by 2, full stop. So this is now another factor of 2. So this is overall 8 pi, and then lambda bar squared. So this is how the cross-section would look like at the maximum of the resonance, okay? Where we impose that the energy of the center of mass is exactly equal to the energy of the resonance. Okay. Now, this we can further write. So let me remind you that the Debris wavelength reduced is just h bar divided by p. This we can also always write as h bar c divided by p times c. So this we can eventually write as 8 pi. Then we have h bar c squared divided by p squared center of mass times c squared. Okay. Now, in the center of mass frame, the momentum of the incident pion needed to reach the maximum of the resonance is exactly p pi cm equal to 228 MeV. Okay. So we can now substitute into our cross-section at the maximum. And we obtain 8 pi, let me just rewrite this, h bar c squared divided by p squared pi center of mass c squared. That is 8 pi. Now, in the numerator, we know that this term is approximately equal to 200 MeV per Fermi, so 0.200 JeV per Fermi squared, divided by the squared of this pion momentum in the center of mass, so 0.228 GeV squared. Once you do this calculation, you would obtain 18.8 Fermi squared. But since we are dealing with a cross-section, we want to translate this into barn, right? So first of all, we commute this into square centimeter. So this is 18.8 10 to the minus 13 centimeter squared. This is now 18.8 10 to the minus 26 square centimeter. Now, let me remind you that 1 barn is 10 to the minus 24 square centimeter. So this is indeed 18.8 10 to the minus 2 barn, or if you like, 188 millibarn. So this is the absolute value of the cross-section at the maximum of the resonance that we just obtained by substituting all our knowledge into the Breit-Wigner formula, and by assuming that the spin, so that the angular momentum of the resonance is 3/2. Okay. Now, it is interesting to note that this is in excellent agreement with the experimental value. Excellent, agree with experiments. And this we can see already in the next slide. So let me now switch back to the slide. So the curve is the Breit-Wigner formula that we just used. The data are experimental, the points are experimental data, and indeed, when you look at the maximum, you indeed exactly obtain, also from the experimental point of view, 188 millibar. Of course, this was based on our assumption that the total angular momentum of the resonance was 3/2, but any other assignment of J would lead to a different value of the cross-section at the maximum. For instance, if we would have been using 1/2 instead of 3/2, then the total cross-section would be 94 millibars. So the maximum would stay somewhere here, okay, which is clearly inconsistent with the experimental data. And in addition to that, the J equal 3/2 assignment is also confirmed experimentally by studying the angular distribution of the final state by the center of mass, which you can describe in terms of Legendre polynomial. Now, the last word about this resonance. So the delta plus plus is a UUU baryon. That's why it comes with a double plus charge sign. It is a 3/2 isospin object, as we already studied a few lessons ago, and it belongs to an isospin quartet, okay, or quadruplet, if you like. The delta plus, so in addition with delta plus, delta zero, and delta minus. You see here now the Quark content. So UUU, UUD, UDD, DDD, okay, which is part of the baryon decuplet that we studied last time. And this resonance can be obtained both in formation, okay, so you can form it from the initial state particle and then decay in the final state, or in production when it is produced in addition to other particles, for instance, pi0. Okay. This diagram here shows you essentially how the quark flavor flows in this reaction. Okay, so you start with the proton with the UUD quark system and the pi plus with a UD bar. Then essentially you annihilate your DD bar pair, and you end up with your intermediate state, the UU bar, which is our resonance, which then further decay into the final state, where you now create from the vacuum a new DD bar quark pair. Any question? Okay. So, so far we discussed about elastic processes, okay? But of course, one can also produce resonances in inelastic processes. So, if the resonance is now formed in an inelastic process, where essentially the final state particles are different from the initial state or are excited state of the initial state, then the Brett-Wigner formula must be modified slightly, okay, to account for the different initial and final states, okay? So let's consider the example of the J-psi production, the way it was discovered, okay, as luck. So E plus E minus into J-psi that decays into hadrons. So we now describe these in terms of our Breit-Wigner function. We have our usual kinematic factor, we have the spin multiplicity, we have these Breit-Wigner dependence in the denominator. And the only difference with respect to the previous expression is that now we don't have gamma square on top of this, but the gamma square has been substituted by the product of gamma EE and gamma H, where gamma EE is the formation width of the J-psi resonance, and it coincides with the decay width of the J-psi into E plus E minus, and similarly for the hadronic contribution. So we know that what we have here. So we can replace here the value of the spin here, and at the end we end up with this compact form. Okay, we also replace here the spin 1/2 for the two particles, etc. Okay. Now this ratio here, so lambda EE divided by lambda, so you have essentially one of these numerator and the total in the denominator, is nothing else than the branching ratio that we know already. Okay, for this decay mode. So it's the probability that our J-psi decayed into the E plus E minus mode. And similarly, the gamma H divided by gamma denotes the branching ratio for the hadronic mode. Okay. Hadronic means that it decays into quark pairs that then, as we will study next week, fragment into final state hadrons. Okay. Now, at the resonance, when the center of mass energy coincides with the mass of the J-psi, then okay, this term drops here, and the cross-section at the maximum is reduced to this very compact form here, okay? And you just have to substitute here, okay, your reduced debris wavelength and the two branching ratio, depending on your final decay mode here. Okay, and once you substitute this and you compute, you obtain the value in absolute units of the cross-section at the maximum, okay, which is in this case 0.07 millibar. So let's now make use of these to solve a problem, again, about non-elastic resonant process. Okay. So the problem is the following. Using the Breit-Wigner formula, calculate the cross-section for the resonant reaction, E plus E minus into pi plus pi minus pi 0, studied at a symmetric E plus E minus collider, tuned to the omega meson peak. So the center of mass energy of the collider is exactly the mass of the omega meson, and making use of the following information. So we know the branching ratio of the omega into E plus E minus, the branching ratio of the omega into the 3-pion channel, which is the Harmonic channel, okay? And we know the mass of the omega. So let's make this. Okay, so this is problem 511. So if you remember from the previous lesson, last week lesson, the omega meson is a ground state vector meson, okay? So the omega meson is a low-lying state, so L is equal to 0. It is a vector meson, so spin is equal to 1. And so the J omega is, in general, L plus S is 1. Okay? And so the multiplicity term to J omega plus 1 is just equal to 3. Now, let's consider now the spin terms. So we have on the denominator, if you remember, we have 2s e plus minus 1 times 2s e minus 1. Of course, the spin of electron and positron is 1/2. So this is 2 times 1/2 plus is plus 1. Sorry, plus 1 times 2 times 1/2 plus 1, and this is equal to 4. What about now the de Broglie wavelength? So our reduced de Broglie wavelength is in general h bar divided by p, okay? And since at the omega mass region, the electron and positron are relativistic, this is essentially equal to E over C. So we can neglect the mass of the electrons in the relativistic energy momentum formula, okay? Now, we also know from the text that this measurement is done at a symmetric collider. So we can put C on the numerator. And for a symmetric collider, we know that the energy, the incidence of each beam must be equal to half the center of mass energy. And we also know that the energy of this machine is tuned to the mass of the omega. So this is h bar divided by m omega divided by 2. Okay? And so finally, we can write this as twice h bar c divided by the mass of the omega meson. This is our reduced de Broglie wavelength. So, we are now essentially preparing all the ingredients. Then we will cook our Breit-Wigner. At the peak, so at the maximum, we have that the energy of the center of mass must be equal to the mass of the omega. And so E minus mr must be E minus m omega, which must be exactly 0 at the maximum. Okay? And now we can put everything together. So let me write now the Breit-Wigner cross-section for E plus E minus into a resonant omega meson that decays into a pi plus, pi minus, pi 0. So this is in general pi, lambda bar squared. Then we have 2j omega plus 1 divided by 2 s e plus 1 times 2 s e minus plus 1, and then we have the Breit-Wigner term since it is an inelastic, okay, so the final state particle are different than the initial state particle, then we have to use it gamma EE and gamma pi 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 in the numerator. Then we have E minus mr squared plus the total width squared divided by 4. So at the maximum, of course, this guy in the denominator disappears, and so we are left with pi. Now we substitute 2h bar c divided by the mass of the omega meson squared. Then we have the multiplicity spin factor, which is 3 divided by 4. Then we have an additional factor 4 coming from the denominator. And then we have essentially the product of the two branching ratios, gamma E over gamma times gamma pi 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 over total gamma. This we can write in a more compact way as 12 pi divided by the squared mass of the omega meson. Then we have h bar c squared, and then we have the two branching ratios, E times branching ratio for the 3 pi state. Let's substitute. So we have 12 pi. The mass of the omega meson is provided by the text, so it's 0.782 GeV squared. Then we have this constant, which is 0.200 Jev per Fermi squared. Then we have the two branching ratios, which are provided by the text. So 7.3, 10 to the minus 5 times 0.892. The result of this calculation is 1.56, 10 to the minus 4 Fermi squared. And again, we want to translate this into Barn. So this is 1.56, 10 to the minus 4, 10 to the minus 13 centimeters squared. It is 1.56 times 10 to the minus 30 centimeters squared. Now we convert into Barn. It is 1.56 10 to the minus 6 bar, and so we can write as 1.56 microbarn. Okay. Questions, comments? Okay, if not, we can stop here today. It was a little bit shorter today. And so next week, we'll attack the QCD chapter.
Maybe I have just a question on the previous slide in the beginning of the course, if we have time.
Today lesson?
Yes. When you mentioned the heavier quarks, you mentioned the states corresponding to radial excitations, JP equals 2 plus. I'm not sure I understand what that means.
This means that besides the low line state that we just quoted today, of course, you have all possible radial excitation. So this means corresponding to higher value of the orbital angular momentum, and so of the total angular momentum.
And those, they're radials, they're symmetric, so the parity is positive. Is that why it was a 2 plus? That's the...
For the let me check, where are we now?
Slide 5, I think.
Okay, in the front. Okay. 5, that's it. Okay, 2 plus.
Oh, yes, sorry. Yes.
Yeah, so the parity, okay, you have to calculate accordingly to the value of L. So this is just probably an example. We have an exciter here. We can have many even, you get the plus for the parity. If you have is odd, you get the minus. But you have to combine this together with the spin. So it depends if you have a spin 1, spin 0. So.
Okay.
All right. So see you not on Wednesday, but on next Thursday, and then on Friday. Okay. And next lesson will be in presence. So I will be in the classroom. So of course you are all invited who can come to come to the classroom next week. Okay.
Okay. Thank you.
Okay. Have a nice weekend.
Thank you. Bye.
Bye bye.
Goodbye.
Bye.